All right, we're going to be beginning chapter 10 today. We're just coming off the heels of doing chapters 8 and 9, where we had focused on finding confidence intervals, where we were estimating the location of a population proportion or population mean. And then in chapter 9, where we were doing significance tests, making kind of testing a claim about either a population proportion or a population mean. What we're going to be looking at in chapter 10 are those ideas, but instead of, and we're going to focus here in this first section on proportions, instead of trying to make a claim or test a claim or find the value of a population proportion, we're going to be, sometimes statisticians want to compare two different proportions from two different populations. And so a lot of what you're going to see here today is going to feel like it's similar to what we've done in the last couple chapters, but it's going to feel a little bit expanded because we're going to be doing things for two populations instead of one. Okay, I'm just going to draw your attention here to the homework assignment because it's on an odd page here, this first part. This is a little bit of AP practice where it's sort of a hodgepodge of many different topics that we've discussed, and that's on page 470 there. Okay, so talking about comparing two proportions here, one thing that I just want to mention to you is that when we're taking a sample from two different proportions, those sample sizes and as well as the population sizes do not have to be the same. So if we were wanting to compare say the unemployment rate from two different countries, certainly the population of those two countries don't need to be the same. And then my sample sizes also don't need to be the same. So maybe from one country, I would take a sample size of 100 people. And then from the other country, maybe my sample size would be 300 people. Okay, so let's start with something that looks familiar here. We had talked in chapter 7, we were first introduced to this notion of a sampling distribution for, notice here, this is for a single sample proportion, okay? So this is assuming that we're reaching into just one population. We're pulling out a simple random sample of size n from that population, and we're calculating a p-hat, some proportion, usually it's a categorical variable here, proportion from that sample proportion, okay? So we would calculate that, we would put that on a dot plot. Each of these p-hats over here represent a sample proportion from one sample taken. And we would do that repeatedly, and it would build what is called a sampling distribution. Okay? And we had learned before that to get the center of your sampling distribution, the mean of the sampling distribution is essentially exactly spot on with whatever the population proportion is. Okay? That's an unbiased estimator. The spread is found by using this formula, which is on the formula sheet here. Okay, and this is where we would often, though, need to make sure that we're careful and that we have first done the 10% condition to show independence before we calculate the spread there. Okay, and then the shape, we can conclude that the shape is approximately normal provided, there's another condition here, this is called the large counts condition, when we show that the number of expected successes as well as the number of expected failures is at least 10. Okay, now that's what we've done before with one proportion. We're going to kind of extend that to finding the difference in two sample proportions coming from two different populations. Okay, so let's take a look at the center, okay? If we're talking about the center of a sampling distribution where we're finding the difference between two sample proportions, essentially what this is saying is you're going to reach in and take a simple random sample from population 1, calculate that p-hat, we're going to call that p-hat sub 1. We're going to reach into a second population, take a simple random sample of the second population, we're going to call that p-hat 2, and then we're going to subtract to find what the differences are in those two sample proportions. Whatever that difference is, that's what would be represented as a dot over here in this dot plot. And we would repeatedly do that over and over again, drawing out one sample from each population, calculating the population or the sample proportion, and then we would subtract those, come up with the difference, plot the difference. Okay, you're going to notice something very similar here, and that is the mean or the center of those differences should be spot on with whatever the true population proportion differences are. Okay, the spread, you'll notice this should look similar to what we had up here for our spread. I'm just going to erase this because it's a little bit hard to see there. Okay, this was on the formula sheet for how to get the standard deviation of just a sampling distribution for p hat. If we want the standard deviation of a sampling distribution for the differences in two sample proportions, you'll notice this just feels like this is an extension of this formula up here. Okay, and essentially what we have is we have the population proportion of a success times the failure divided by the sample size. And so we're doing that for each population, and we're adding those together, taking the square root. Okay, once again though, please make sure that you're careful. You have to show that the 10% condition is met for each population. Okay, you have to show for both populations. Okay, and then finally, the shape. We could say that the shape is approximately normal for the sampling distribution of the difference between the sample proportions, provided we've done the large counts condition for both the first population and the second population. Those both have to be at least 10. So like up here, we only had to do it, the number of expected successes and number of expected failures were at least 10. We have to do that for each population. Okay, so let's go ahead and flip to the next page here. We're going to take a look at sort of what this looks like here with this first example. It says to explore the sampling distribution of the differences between two proportions, we're going to start out with two populations having a known proportion of successes. So we're going to assume we know what the parameters are here. At school number 1, 70% of students did their homework. Okay, so we're going to say this is not a p hat, this is everybody in the whole entire school was surveyed. This is a population proportion, 70% did their homework. Okay, at school 2, 50% did their homework. So this again is a parameter. Now it says, let's suppose that the counselor at school 1 takes an SRS of 100 students and he records the sample proportion out of that 100 who did their homework, okay, which may not be exactly 70% if we're just taking one simple random sample of 100 students. Okay, for school 2, their counselor is going to do the same thing, except they're just going to take a sample size of 200 students. Okay, remember the sample sizes don't have to be the same from each of the populations. Okay, as you look at these graphics below, what we're seeing here in these graphics is we're seeing that if these counselors were to repeatedly do that 1,000 times, so from school number 1, they're going to do 1,000 samples of size 100. They're going to ask them, how many of you did your homework? Calculate that proportion. That's what we're seeing right here. All these dots represent, those 1,000 dots represent the proportion of students who did their homework from each of those samples. Okay. Then counselor 2 also does 1,000 simple random samples, size 200. That's what we're seeing in this middle dot plot here. Okay. Now, looking at these separately, we had learned in the previous chapters here that to get the shape, okay, we would have to show the large counts condition where the number of expected successes, so that would be sample size times the known proportion here, 0.7. 70, that feels like that is definitely greater than 10. And then we would have to show that the number of expected failures, 100 times 0.3, which is 30, greater than or equal to 10. So we could conclude that it is definitely approximately normal. Okay. The center should be spot on with what we know the true population proportion to be. And you can kind of get that sense right here that the center of the sampling distribution feels like it's right there at 0.7. And then the spread, the formula is the probability of a success times the probability of a failure divided by the sample size, provided that we're doing the 10% condition. You can see that here. We're taking 10 times the sample size. That total needs to be less than or equal to what the entire population is at school 1. And I think we're assuming that there's more than 1,000 students at school 1. Okay, we could say essentially the same thing here for describing the shape, doing that large counts condition here for school 2, the center, as well as the spread, doing the 10% condition. Okay, and we can see the center there feels like it's about at that 50% mark. Okay, what we're going to be focusing though on this section is we're going to be focusing over here at this third graphic, where what you have pictured here at this third graphic is where every time this first counselor draws out one sample and every time the second counselor draws out one sample, we would be subtracting the difference here, p hat 1 minus p hat 2, and we would plot that difference as a dot over here on this grid. Okay? Now, to conclude that it is approximately normal, we would have had to have shown that each of the two populations were approximately normal. And we did that already over here by checking the large counts condition. So I'm just going to make a note. This is approximately normal because the number of successes and number of failures are all greater than or equal to 10. Now, you'd never be able to say just that without showing the work here, but we have the work right here to look at. So there's 4 things you have to show. Okay, you have to show each one successes and failures are greater than 10 for both populations. Okay, the center. Now, the center of this sampling distribution for the difference in p hat 1 minus p hat 2 is just simply subtracting in that order these two means. Okay, so the center would be, the difference is roughly 20%. Okay, now for the spread, again, with the spread, there is a condition, the 10% condition. You'd have to show that that's met for each of the two individual populations, which we already did here. So we can use the formula. Okay, and this is just an extension or an expansion of the other formula here. We take the probability of a success times the probability of a failure divided by the sample size for population 1. And then we do the same thing here for population 2. Probability of a success times probability of failure divided by the sample size. Okay, so we label this the standard deviation for the difference in the population proportions for that sampling distribution. It comes out to 0.058. Okay, so what does this standard deviation for the difference in the sampling proportions mean when we say it's 0.058? Well, what that means, think about when we interpret standard deviations, it means the difference in the sample proportions of students who did their homework at the two schools, the difference will typically vary by about 0.058 from what the true difference in the proportions are, like the actual difference between the two proportions, okay? All right, so let's go ahead and flip here to the next page, and we'll see if we can try to put this in action with an example here. And so what you see here is just reiterating the center, spread. I'm just going to highlight that when we do the spread, we have to do the 10% condition for each, and the shape, okay, which means okay, and we were saying here that we just need to make sure that when we're doing the shape, we're doing the large counts condition, but we're doing it for both populations. And so we need to show all 4 things, number of successes, number of failures for each population is at least 10. Okay. Now, it's also just important to note here that when we're doing this, we need to make sure that our samples that we're taking from each of these populations are independent of each other, that the two populations aren't intertwined in some way. They need to be independent random samples. Okay, so let's look at example number 1 here. What we're going to be focusing on right now is we're going to be focusing on describing the distribution for the differences between these sample proportions. And anytime you're asked to describe a distribution, what they're after is they're essentially after you describing the shape, which is often going to be normal, if we can show that large counts condition, the center, and then the spread, which will do the 10% condition. And so the idea with this example, it says your teacher brings 2 bags of colored goldfish crackers to class. Bag 1 has 25% red crackers, and bag 2 has 35% red crackers. Okay, now these are not samples. This is actually sharing with you the population proportion. So we're going to say bag 1 is 25% red crackers. The proportion in bag 2 is 35%. Okay, each bag contains more than 1,000 crackers. So the reason they shared that information is when we do the 10% condition, we know how many crackers are in each bag's population. It says using a paper cup, your teacher takes an SRS of 50 crackers from bag 1 and a separate SRS of 40 crackers from bag 2. So I always like to write down the information that you're given. Our sample size for population 1 is 50. The sample size being taken from population 2 is 40. Okay. Now for part A, it says what is the shape of the sampling distribution for the difference in the sample proportions and why? Well, when we're asked to describe the shape, we need to be thinking large counts condition. Okay, so it's good for us to sort of separate this since we're talking about 2 populations now instead of just the 1. So for bag 1, I need to show that if I take the sample size of 50 times the probability of a success, which is the probability we get a red cracker, that total is definitely going to be at least 10, and then that 50 times the probability of a failure, 75%, not getting a red cracker, is also going to be at least 10. Okay, so that checks off good there. I'm going to do the same thing over here for bag 2. Okay, and this is just sort of the tedious part to this. I know this is tedious. The graders need to see that you are showing that these conditions are absolutely met. You cannot just write down and say, number of expected successes and failures for both populations is at least 10. They need to see these substitutions. They need to see that you've done these calculations. And then our conclusion, we know that when we draw these 3 dots, that means therefore it is approximately normal. Okay, the shape for this sampling distribution. Okay, part B is asking us to find the mean of the sampling distribution. Okay, now there really is not a condition for us to show for this. We just know that the mean, or the center, would be the difference in whatever the population proportions is. Okay, so we know that when we take the difference in the proportions of red crackers, that it's a little less than 10% is that difference there. Okay, and then for our standard deviation, it's asking us to find the standard deviation. So we want to be thinking here that the standard deviation, we need to be tying that directly to the 10% condition, which I kind of typed here. Okay, remember our sample sizes are 50 and 40. So we need to show 10 times 50, which is 500, and 10 times 40, which is 400, is technically less than or equal to the 1,000 cracker population size. Okay, once we've showed that, that means our independence condition is met. We can then press forward here with the actual formula. Again, this formula is on the formula sheet here. Okay, but make sure our denominators are the sample sizes, and the numerator is the probability of a success times the probability of a failure. Once we have that, we would be describing our distribution here as normal. This is the difference between these population proportions. There's the center, that's the mean, and this is the standard deviation. All right, on the next page, this will be the last example that we're going to do for this video. We're going to be talking about American-made cars. We're talking about Nathan and Kyle. They both work for the Department of Motor Vehicles, but they live in different states. Okay, so the states are kind of like the different populations. It says here in Nathan's state, 80% of the registered cars are made by American manufacturers. So I'm just going to write down the information as I'm giving it here. And they're giving this to you as this is a population proportion. Okay, so the P sub N for Nathan's state, 80% of those registered cars are American manufacturers. In Kyle's state, P sub K, 60% of the registered cars are made by American manufacturers. Nathan selects a random sample of 100 cars. Okay, so from population 1, sample size is 100. Kyle selects a sample of 70 cars from his state. Okay, we're going to let P hat sub N minus P hat sub K, so we're taking Nathan's proportion minus Kyle's proportion, be the difference in sample proportions of American-made manufactured cars. Okay, we are asked in number 1 to find the center of the sampling distribution and state the condition that guarantees your answer. There is no condition that you need to show for finding the center. Okay, so the center of our sampling distribution for the difference in Nathan's minus Kyle's sample proportions would be just that, subtracting their population proportions, we get 0.2. Okay, you always want to show the condition first, if there is one to show, before you do the calculation. Okay, for number 2, it says find the spread. So I immediately need to think, okay, spread, this is going to be my 10% condition. Okay, so for 10% condition, I have 2 different populations. I need to show 10 times the sample size in Nathan's state. That's 1,000. That needs to feel reasonable, that that is less than or equal to all the American-made cars in Nathan's state. And then 10 times the 70 sample size would be less than or equal to all the American cars in Kyle's state. Okay, so that feels reasonable, that there's definitely more than 1,000 cars or more than 700 cars in each of their states. So that means we can kind of check off that the independence condition is definitely met. Okay, so we can move forward with then doing our calculation for the standard deviation for the difference in these sample proportions. Okay, so we're doing probability of a success times probability of a failure divided by sample size plus same thing for the other population. Okay, there is our standard deviation. Okay, finally down here for C, we are asked to find the shape. Okay, I see shape, I need to think, okay, now this is large counts condition, so I need to show that I'm doing N times P is 80, N times 1 minus P, 20. Kyle's state, N times P, 42, N times 1 minus P, 28. I'm going to make the remark that all are greater than or equal to 10. Okay, you need to make sure that you mention something. You could put greater than or equal to 10 after each of the numbers or just make that statement there. So then I can conclude, therefore, approximately normal. All right, so we should now be able to answer this question here at the bottom. We want to find what is the probability that the sample proportion of cars in Nathan's state is more than 10% larger than the sample proportion of American cars in Kyle's state. Okay, so we're talking about, remember the order we did this subtraction here, we were doing N minus K. Now let me just go ahead and take the information we had calculated up above. Okay, remember this is doing Nathan's minus Kyle's. Okay, here's what we got for our center and our spread here. Okay, the question is, what's the proportion what's the probability rather, that difference, okay, that difference, we can call it X if you like, is greater than 10%. Okay, well, let me draw a curve here. Down the center, we're going to put what we know the average differences in the sample proportions. That's 0.2. Okay, we're looking for that it's greater than 10%, so I'm putting 10% over here, then I'm going to be shading to the right because it's greater than. Okay, I'm going to do my normal CDF calculation. I'll put my blanks underneath here since I'm running out of space. Okay, we got to put these labels, lower, upper, mean, and standard deviation. Okay, 0.1, 10,000, 0.2, 0.0709, and this ends up coming out to 0.9208 or 92.08%. Okay. You can see the assignment or those review problems on page 470 as well as two problems that kind of